Okay, so part 2, now we're on to verifying trig identities. I know you can tell by the inflections in my voice that I'm incredibly giddy right now because, again, this is my favorite part of trig, and there you hear the thunder in the background perhaps, and you can feel the excitement. So, now you can see the 4 examples you're going to do. I want you to pause the video, try to verify these identities, unpause it when you're ready to finish. Real quick, just to remind you about how this is done. So you only work with one side of the equation. You can choose which side you want to work with, but only work with one side. You are trying to prove that that side does actually equal the other side. I will never give you one that doesn't actually work. That would just be mean. So it's basically the same exact thing you were doing with simplifying, except for now you know what the outcome is going to be. So it's a proof, like in geometry, except for you don't have to justify the reasoning, you just do substitution in algebra. So now pause the video, unpause it when you're ready to check your work. Okay, so if we look at this first one here, I chose to work with the left-hand side, so it has to be a conscious decision. I'm choosing to work with the left-hand side. My thought process, I notice on the right-hand side all I have is cosine and a -1. So on the left-hand side, how can I change sine squared into something with cosine? I know the Pythagorean identity tells me sine squared is 1 minus cosine squared. I distribute the negative, and I get my answer of 2 cosine squared x minus 1. You may also recognize, again, these are the double angle formulas for cosine. Again, I don't expect you to use the double angle right now, but I want to just point that out, that both of these are cosine of 2x and cosine of 2x. Again, I don't expect you to use that right now, but I want to point it out. Now over here for the second one. So this is not the only thing to do, but what I chose to do was to work with the left-hand side. Now, your strategy for how do I know which side I want to work with? Usually, although this sounds counterintuitive, usually you want to work with the side that looks more complex. So in this first problem here, they both were about the same. On the second one, though, the left-hand side of the equation definitely looks more complex than the right-hand side. So it's going to be easier for me to work with the more complex side. It's easier to take something complex and simplify it down than it is to take something that's simple and expand it into something complex. Okay, so first strategy was get everything in terms of sines and cosines. Since I have a cosine, a sine, and a tangent, change tangent into sine over cosine. At the same time, get a common denominator. So I have 2 terms here. This one is going to have a denominator of cosine, so multiply the cosine by cosine over cosine to get a denominator of cosine as well. The reason why I know that's a good idea, since I have 2 terms and my answer is just 1 term, I know that I want to combine these somehow. The best way to do that, get a common denominator. So now the numerator becomes cosine squared plus sine squared. Denominator is just cosine. Cosine squared plus sine squared is 1. 1 over cosine is secant. Bam, I'm done. Down here on the left, so I chose to work with the left-hand side. This is an example of a problem where it's just as easy to work with the right-hand side also. So what I did first was get a common denominator. Again, I realized that on the left-hand side of the equation I have 2 terms. On the right-hand side I have 1 term. In order to combine 2 terms into 1, you need to be able to get a common denominator. So multiply the top and the bottom by sine, and I end up with 1 minus sine squared over sine. 1 minus sine squared is cosine squared. So I'm done. Now just to point out, you could have followed the same exact logic on the right-hand side, but done it in the opposite order somewhat. So I could have gone from cosine squared of x over sine of x into 1 minus sine squared of x over sine of x. So I could change cosine squared into 1 minus sine squared, and then I could split up this fraction, because it has a single denominator, into 1 over sine of x minus sine squared of x over sine of x, which is just sine of x. Then the last one. So here, just like with the cofunction identities, if you see a cofunction identity, use it or change it right away. If you see an even-odd identity, which means that you have a negative variable for the angle, change that right away. That's always what you want to do first. After that, it's your choice, but get rid of the negative angles. So cosine of negative x is cosine of x, sine of negative x is negative sine of x. So this became cosine of x over 1 minus sine of x. Now I chose the strategy that I did before on one of the simplify problems, and that is multiply the top and the bottom by the conjugate of the bottom. The reason why I know this is a good idea here, look at what's on the right-hand side of the equation. The right-hand side of the equation has two terms separated by addition. If I multiply by the conjugate, I know I create the difference of squares in the denominator, which will simplify to a single term through a Pythagorean identity, and I created addition in the numerator. So those are good things. So now the numerator stays 1 plus sine of x times cosine of x. Again, don't distribute the cosine. How do I know that I don't want to distribute it? Well, you're not positive, but again, there's nothing that I know. I know 1 plus sine times cosine is not going to simplify in any way. The denominator becomes 1 minus sine squared of x. 1 minus sine squared of x becomes cosine squared of x. The cosine squared and the cosine in the numerator reduce. So I'm left with 1 plus sine of x over cosine of x, and now I can split up the fraction. So this becomes 1 over cosine of x, which is secant of x, and sine of x over cosine of x, which is tangent of x, and there's my addition that I wanted. So I'm done. That's not the only way to do the problem. There are other methods. For instance, after I use the even-odd identities, if instead of multiplying by the conjugate of the denominator, I multiplied by cosine over cosine, I would have created a cosine squared in the numerator. Then I could factor that into 1 minus, or I could substitute and make that 1 minus sine squared, factored into 1 plus sine of x times 1 minus sine of x, and basically the same process would have happened. But again, it's just a different strategy in which you could have taken. Okay. So simplifying trig expressions, we want to factor, we want to multiply, we want to add or subtract fractions with the least common denominator, split a fraction into multiple terms, combine like terms, and substitute identities. So these are the same strategies we want to use when verifying trig identities as well. We just know what the answer is that we're trying to get to.